Take a look at a topic called integration by substitution. A lot of times we refer to this as u-Substitution. The way you kind of want to think about this is it's basically the undoing of a chain rule derivative. We're working backward. Okay, a lot of what we've been talking about with our antiderivative or integral rules has been undoing a specific derivative rule or working backward. Same with this. And just like before, if we have a substitution problem, we want to identify what piece of this is our u and then take the integral of that. The big pieces that we have to make sure to account for our du, the derivative of the u function, because there has to be a constant multiple of that in order to be able to take the integral. There's sort of two ways to kind of think of this. You're taking the integral of f of g of x, which would give us the antiderivative of f of g of x plus c. You can also kind of think of it with your u, which might be a little bit helpful if you have f of u, where u is some function of x. And again, the key there is having the du, so the derivative of the u, in the equation. That would give us the antiderivative of that function of u plus c. And again, probably not going to make a lot of sense when you first see this. It's going to make more sense once we go through some examples. So let's take a look. Kind of as a general rule, just like we did when we did chain rule with derivatives, a lot of times we talked about to figure out what is our u was to look in parentheses, to look in square roots, to look in radicals of any kind, to look in denominators sometimes. Same thing is going to be true for integration using u-Substitution. It is sometimes the most complicated part of the integrand, what is inside the integral, and a lot of times it might be in parentheses or a denominator or a radical of some kind, and that's kind of your clue that, hey, this is what's different. Also, it's a clue when we can't take the integral, when you look at it and say, I don't have a rule for this problem. So, for example, number 1 here, we do not have a rule for this type of problem. We have sine of x over square root of cosine of x. So if we think about this one, okay, we want to take the integral of this function. If we make our u what's on the bottom inside the square root, cosine of x, then our du, which is the derivative of u, would be derivative of cosine of x, which is negative sine of x, and then we want to put dx with it because we took that with respect to x. Okay, all right. Once we have our u and our du, we want to rewrite the integral in terms of u. So let's think about what we have. We have square root of cosine of x on the bottom. In terms of u, that's a square root of u on the bottom, which we could write as u to the negative 1/2. Now let's think about what's left. We took care of the square root of cosine of x with that u to the negative 1/2. We have sine of x dx left in our expression. Take a look at our du. Du is negative sine of x dx. So we have negative du. We have the opposite sign. So we have u to the negative 1/2 times negative du. Now we can take that integral because that's an easy integral to take. Now it's an easy expression to work with. Okay? We have that negative, which is just the sign. Now think about u to the negative 1/2. When we take an integral of something to the negative 1/2, that becomes u to the positive 1/2 when we add 1 to the power. And then we're going to divide by 1/2, which means multiplying by 2. So that gives us negative 2 u to the 1/2 plus c. Last thing we need to do is go ahead and plug back in our u. That would be negative 2 times cosine of x to the 1/2 plus c. And that would be our final answer. You could make that a square root if you wanted to, negative 2 square roots of cosine of x plus c, and that would be fine as well. Okay. Also remember, you could quickly take the derivative to work backward, make sure it ended up giving you what you had originally, which this one would. Okay. All right, let's take a look at the next one. We want to take the integral of 3x squared times square root of 2x cubed minus 5 dx. Again, This one doesn't fit a set rule. This is not one that we have a set rule for. We have two things multiplied here, so that's part of our clue that, hey, I need to do something different. Okay, and again, we do have a radical, so most of the time what's in your radical is going to be your u. So let's say we make u be equal to 2x cubed. If I could write, whoa, that was not it. Okay, 2x cubed minus 5. Then our du, the derivative of that would be, 6x squared dx. All right, next thing we want to do is rewrite this integral in terms of u. So let's think about what we have. The easiest thing to deal with is always the actual u. So that's our square root of 2x cubed minus 5. If u is 2x cubed minus 5, then that piece represents the square root of u, which we could write as u to the 1/2. Okay, now we've taken care of this piece. That's what u to the 1/2 represents. Take a look at what we have left. We have 3x squared dx. Our du is 6x squared dx. So think about, what do we have in terms of du? We have half of the du, right? Okay, we have half of that derivative. We have 3x squared dx, which is half of 6x squared dx. So we can say it's times 1/2 du. When we take that integral, 1/2 is just a constant, so let's leave that there. Now let's take the integral of u to the 1/2. Integral of u to the 1/2 becomes u to the 3/2, right? We divide by 3/2, which means we're multiplying by 2/3, and we need our plus c. If we simplify here, 1/2 times 2/3 becomes 1/3. Now let's plug back in our u. We have u to the 3/2, which is to the 3/2 plus c. And that would be our final answer. And again, we could take the derivative of this if we wanted to. Notice that would give us 3/2 times 1/3, which would be 1/2 times 2x cubed minus 5 now to the 1/2 times 6x squared. The 1/2 times the 6x squared would become 3x squared, and we would have our original function. All right, let's try another one. Okay, again, we have a product here. Now we have two items that are in parentheses. Okay, and so my kind of hint here would be, first of all, is one more complicated than the other one? Okay, and is there a multiple of the derivative of one of them? Notice that 2x plus x squared is to the 5th power. So that one looks a lot more complicated than the 1 plus x. So let's try setting our u to be 2x plus x squared. Okay, if we do that, then our du, the derivative of our u, would be 2 plus 2x, and then we want dx because that was the derivative with respect to x. Now let's take a look at what we have here and rewrite in terms of u. The 2x plus x squared to the 5th is u to the 5th power. Okay, so we took care of this piece. Now we have 1 plus x times dx. Take a look at our du. Our du is 2 plus 2x. If we divided that by 2, we'd have 1 plus x times our dx, right? So this 1 plus x dx is 1/2 of the du. Now we have everything in terms of u, and we can take that integral. So 1/2 is just a constant. Integral of u to the 5th would be u to the 6th over 6, and then we need plus c. So let's rewrite this with our u plugged back in. 1/2, and then we have 6 on our denominator, so let's multiply. 1/2 times 1/6 gives us 1/12. Then we have u to the 6th power, so that's 2x plus x squared, all to the 6th plus c. All right, take a look at number 4. We have integral of x times secant of x squared times tangent of x squared dx. Now, this one, we've got some trig and we've got some regular x functions here. My clue about what I would be doing is I know that I can take an integral of a secant times a tangent, right? We know that integral of secant tangent. The difference here is that we have secant of x squared and tangent of x squared. Okay, so x squared is our different piece, is our piece that makes this harder to take the integral. It's also inside the parentheses. So what if we make our u x squared? Our du would be 2x dx. Okay, if we try using that, let's rewrite in terms of u. The secant of x squared times tangent of x squared, we could say is secant of u times tangent of u. Now we've taken care of this piece and this piece. All we have left is x dx. So think about what we have. Du is 2x dx, so we have 1/2 of that. So we're going to say this is times 1/2 of du. 1/2 is just a constant, so we're going to take that out front. Now, we know that the integral of secant tangent, secant times tangent, is secant. Okay, so the integral of secant times tangent is secant. 1/2 secant of u plus c. Now let's plug back in our u. That would be 1/2 secant of x squared plus c. Now think about taking that derivative to work backward and check. We'd have 1/2 times secant of x squared times tangent of x squared times the derivative of the x squared, 2x, which would end up giving us that original function. Okay, so we could quickly check that with the derivative. All right, let's try some definite integrals this time to see if we've got this. Okay, we want to evaluate the integral from 0 to pi of cosine of x over 2. So the first thing that I want to do is go ahead and get that integral expression. Okay, in order to do that, let's think about what u would be. Well, what's different about this equation? We know how to take a derivative of cosine of x, right? But the different thing about this one is we have x over 2 instead of x. So if our u is x over 2, which is the same as 1/2 x, then our du, the derivative, would be 1/2 dx. So if we rewrite this integral in terms of u, we've got cosine of u, and that takes care of this piece. Then we just have dx, which is like 1 dx. Okay, if our du is 1/2 dx, then that means we have 2 times the du. If we were to take that integral of cosine is sine, so we're going to have 2 sine of u, which is x over 2, and then we would have plus c, but this is a definite integral. So this is going to become 2 times sine of x over 2, and we're going from 0 to pi. So that's 2 times sine of pi over 2 minus 2 times sine of 0. Okay, we know that sine of pi over 2 is 1, right? Let me move this out of our way. Sine of pi over 2 is 1, so we have 2 times 1, which is 2, minus 2 times sine of 0. Sine of 0 is 0, so 2 minus 0 gives us 2 for the final answer here. Number 6, we have integral from 0 to 1 of x squared times x cubed minus 2 all to the third. So for this one, again, we have two things multiplied, so that's our clue that this is a little bit different, and we can't just distribute because all of that's to the third power inside the parentheses. So again, kind of a clue for our u is probably going to be whatever's in the parentheses. So let's make our u x cubed minus 2. That would make our du derivative 3x squared dx. Now if we rewrite in terms of u, this x cubed minus 2 to the third is u to the third. Then we have x squared dx left. Think about what that is. That's 1x squared dx. That's a third of the du. So we have times 1/3 du. Okay, so let's take that integral. 1/3 is just the constant, and then u to the third becomes 1/4 u to the fourth. Okay, and that would be, plus c. However, this is a definite one, so let's rewrite this. 1/3 times 1/4 becomes 1/12 times u to the fourth, so times x cubed minus 2 to the fourth, and we're going from 0 to 1. Okay, so let's plug in. We want to start with 1. 1 cubed minus 2 is -1. Okay, to the fourth minus 1/12 times. Now we've got 0 cubed minus 2. 0 minus 2 is -2. And we have that to the fourth. So let's think about what we have here. 1/12 times -1 to the fourth. -1 to the fourth is 1, so this is 1/12. Minus -2 to the fourth would be positive 16. 16 over 12. We're just going to leave it like that for now. And then we'll simplify when we combine. 1 minus 16 gives us -15 over 12. We can reduce both of those by 3, so that would be -5 over 4. Okay? And again, that's still using our u-substitution, only we have to plug back in the u and then evaluate at our limits of integration. Now let's take a look at a free response problem. Okay, we're going to start here. I think I only put 2 parts here, yes, so we can easily take a look. A particle moves along the x-axis with velocity given by v of t equals cosine of 2t for 0 to 2 pi, and the position of the particle at t equals pi over 4 is 3/2. Okay, part A, at what values of t does the particle change direction? Now for this one, we're not using an integral, okay? Let's think about what we would need to do for this problem. We want to see where particles changing direction, so where velocity is changing signs. So let's take velocity, set it equal to 0. Okay, looking for where cosine of 2t is equal to 0, which means we're looking for where cosine is 0, and that will be what 2t is equal to. Cosine is equal to 0 at pi over 2. 3 pi over 2, and so forth. Let's think about what that would mean for t. T would be, after we divide by 2, pi over 4, 3 pi over 4. We have not reached the end of our interval. We go from 0 to 2 pi, so let's keep going. What would the next solution be for 2t? Cosine is equal to 0 at 5 pi over 2. If we divide by 2, that's 5 pi over 4. Cosine is also equal to 0 at 7 pi over 2, so that means t would be 7 pi over 4, and then that would be the last solution in our interval 0 to 2 pi. All right, so now we want to know where it changes direction, so that means we have to check. We need to check a number line. Are we changing signs at all of these values? So if we plug in something to the left of pi over 4, okay, into the velocity, then cosine is going to be positive. Okay, something between pi over 2 and 3 pi over 4, cosine is going to be, cosine of 2 times that is going to be negative. We plug in something between 3 pi over 4 and 5 pi over 4, such as pi, that becomes cosine of 2 pi, which is positive. If we plug in something between 5 pi over 4 and 7 pi over 4, such as 3 pi over 2, that becomes cosine of 3 pi, which is negative. If we plug in something to the right of 7 pi over 4, that is going to become positive again for our velocity. So notice that our velocity is changing signs around all of these values. So all 4 of these values would be times where the velocity is changing direction. Or velocity is changing signs, so therefore the particle is changing directions. Part B, on what intervals is the particle moving to the left? Okay, for this one, particle is going to be moving to the left when velocity is negative. So we would want to take a look at our number line we already created up here in part A. This number line had to do with velocity, so velocity is negative between pi over 4 and 3 pi over 4, and between 5 pi over 4 and 7 pi over 4. Okay, so we were looking there for where velocity was negative. All right, moving on. Still using the same problem, but now we're going to be looking at part C for an expression for the position of the particle. This is where our integration using substitution is going to come into play, because to find x of t, we have to take the integral of cosine of 2t, the integral of the velocity. So we know x of t would be the integral of cosine of 2t dt. Now, taking a look at this, we know an integral of cosine. The difference here is we have 2t inside the parentheses. So if we make our u 2t, then our du would be 2 dt. If I could fit it there. If we rewrite this in terms of u, cosine of 2t is cosine of u. Then we just have dt left, which is 1 dt, meaning we have 1/2 of du. So if we take that integral, we end up with 1/2 sine of u plus c, which is 1/2 sine of 2t plus c. Then look at our initial condition. We know that x of pi over 4 is equal to 3/2, which would be equal to 1/2 sine of 2 times pi over 4, which would be pi over 2 plus c. That means 3/2 is equal to 1/2 plus c. So if we subtract 1/2, then c is equal to 1. So now we know that x of t is 1/2 times sine of 2t plus 1. Okay. Part D, find the total distance the particle travels from t equals 0 to t equals pi. Okay, so we know we're going to plug in 0 and pi into our equation, okay, into our position equation. However, we also need to check between 0 and pi, was there anywhere where our particle was changing direction? If we take a look at part B, our solution there, or sorry, part A, we said we were changing direction at all 4 of these t values. 2 of them are on our interval, pi over 4 and 3 pi over 4. So we also need to check the position at those places as well, since we are changing direction. So we need x of 0, x of pi over 4, x of 3 pi over 4, and x of pi. Okay, so let's plug in and see what we get. X of 0, if we plug in 0, sine of 2 times 0, sine of 0 is 0, plus 1 gives us 1. Okay, pi over 4, 1/2 times the sine of 2 times pi over 4 would be pi over 2. Sine of pi over 2 is 1, so 1/2 plus 1 gives us 3/2. Let's try 3 pi over 4. 1/2 times the sine of 2 times 3 pi over 4. That becomes sine of 3 pi over 2. Sine of 3 pi over 2 is negative 1. So 1/2 times negative 1 is negative 1/2 plus 1 gives us 1/2. And then x of pi. Let's try this one. 1/2 times the sine of 2 pi would be 1/2 times 0 plus 1 gives us 1. So let's find total distance here by checking in between. Distance from 1 to 3/2 is 1/2. Distance from 3/2 to 1/2 is 1. Distance from 1/2 to 1 is 1/2. If we add up all 3 of those, 1/2 plus 1 plus 1/2, that gives us 2 units. However, notice if you didn't think about where we were changing direction and we just looked at the endpoints of the interval given, it looks like we didn't travel any distance at all, right? Because both of those are at position 1. So again, we have to take into account where a particle would change direction in order to find total distance traveled. Okay, guys, if you have any questions, please feel free to reach out. I hope this was helpful.